We are going to present now the new NVIDIA Grace CPU Superchip and how this will be integrated in our roadmap. NVIDIA is providing a 3 chip in the starting this year. We announced already the Grace CPU Superchip and the Hopper GPU, and this will be paired with the new technology in terms of networking, Bluefield 4. But today we are focusing more on the CPU and GPU innovation that NVIDIA brought to the market. This is a long-term strategy, and we are in plan to go beyond the actual generation in 2025, 2026, announcing already Hopper Next and Grace Next. But let's focus a little bit in the innovation regarding the Grace Superchip. NVIDIA created this new SoC in order to be able to host the next generation challenge in AI and HPC. In fact, this CPU has been designed in order to provide not only very powerful core capability. We are adopting ARM v9 or Neoverse v2 cores with 4 pipeline 128-bit per core of SV2. We design a very fast on-chip fabric with more than 3.2 terabyte per second of bisection bandwidth, and with a very high bandwidth low power memory called LPDDR5X. This is the first time probably that this technology has been introduced for data center SoC, and allow us to provide a very low power platform. In fact, the LPDDR5X is consuming only 20 watt, 20-25 watt, and provide more than 500 gigabytes per second of raw bandwidth. In 2 sides, 128 gigabyte raw and 512 gigabyte raw. This high bandwidth, low power memory is paired with the biggest innovation that we have in this CPU, that is the chip-to-chip connection. The chip-to-chip connection allows us to connect the Grace CPU with another Grace, creating a two socket. If you want solution, very common in HPC, or we can connect this with an Hopper GPU to create a very powerful AI platform. In every case, the Grace CPU is a very extremely energy efficient. In fact, the overall CPU and memory is rated at 250 watt in terms of TDP. Let's deep dive on the NVLink chip-to-chip, because this is a great innovation. We have an access to the CPU at 500 gigabytes per second, as we said, and the NVLink chip-to-chip interface allow us to connect this incredible powerful CPU with another device that could be another CPU or another GPU, really creating a single superchip. A single superchip that is flexible with the same factor. In fact, we are producing two superchip, one focusing CPU only or conventional computer environment for who is not able to move to accelerated computing, and require a conventional platform that has very low power consumption, and this is a CPU-only Superchip. But also we are creating a CPU and GPU module that allow us to create a very interesting platform for very large AI challenges. At the same time, thanks to the memory coherent chip-to-chip interface, this platform is also perfect for HPC because allow application to be ported to GPU without the problem of data management and data movement. In the past, in fact, this was one of the limiting factors to have high efficiency with HPC application, because sometimes the data movement between CPU memory and GPU memory was limited by the PCI Express connectivity. In this case, with 7 times the performance of PCI Gen 5, the chip-to-chip interface and the memory coherency can give us a single page space where developers can easily port their application on this platform without problem and without focusing on overlapping and all these complex techniques to have a very high efficiency and performance. So the NVIDIA Grace platform with 2 Superchip are the perfect match for cloud, AI, and HPC infrastructure.
Let's now talk about software and programming model for the NVIDIA Superchip platform. First of all, I want to mention that NVIDIA has invested a lot of effort in building accelerated libraries over the past decade to empower developers in multiple verticals, including high-performance computing, artificial intelligence, autonomous driving, robotic, healthcare, etc. When we look about Grace and the software ecosystem around it, we have to look at ARM and the software ecosystem around it. Grace is the first ARM-based CPU based on ARM v9 core IP that can be bought and deployed to the data center. But it's not the first ARM CPU. There's a lot of software that have been built on other ARM-based CPUs in the past decade that Grace can use. And NVIDIA contribution here is not just to bring Grace as a product, but also improve and optimize open source software and some vendor-specific software for ARM v9 for other SoC in the future to benefit with. Because Grace is paired with Hopper into the Superchip architecture, then we have our own compiler, accelerated library and framework to program what we call the NVIDIA platform, the CPU plus the GPU together. And with those tools, we can produce and build portable, optimized, and accelerated acceptable that run on CPU and CPU plus GPU for high performance. In the era of HPC, the NVIDIA HPC SDK is the toolbox that allow you to access compilers for Fortran, C, C++, core libraries, mathematical libraries, communicational libraries, but also tools like Profiler and Debugger that allow to give you an idea about what's going on in your code and define and understanding performance even at the lowest possible level. This toolkit is developed for the NVIDIA platform, so for CPU, GPU interconnect is freely available. We release multiple times a year, and yes, it works on ARM alongside other architecture. Through this toolkit, the HPC developer, the technical computing developer, can access multiple programming models to program the NVIDIA platform. If you're aiming for maximum performance, what we call the speed of light, CUDA is the way to go. Access the lowest possible hardware feature, total control, maximum performance. But over the year, we embrace other programming models that can allow developers to be more productive and at the same time accelerate their time to science. We embrace directives, OpenSC and OpenMP specification for incremental and portable optimization and porting of big application, but also to make application jumping from single thread to multi-thread to many core and make them also future-proof. We also embrace the idea of accelerated standard languages. So extension and modern extension of languages like C++ and Fortran that allow to write parallel code that has no resemblance of any GPU code, but thanks to compiler optimization and compiler runtime, being able to be offloaded on the GPU automatically with very little effort for the developer. And this is one of the key pillars, one of the key programming models that get an extra benefit by the Grace Superchip architecture. Thanks to its innovative architecture, we see the Grace Hopper Superchip platform being really good for three classes of application. The one that we classify as a partially GPU accelerated application, a portion of it is offloaded on the GPU and works very well, but there's still some computation happening on the CPU, and often this computation is very much memory bound. There's a second class of application we call PCIe limited, or with a PCIe bottleneck, which means that for whatever reason, there's a lot of data moving back and forth from the CPU to the GPU and vice versa, and that creates a bottleneck %. In this case, a fast C2C link compared to PCIe allows the application to receive a boost in performance, but also a new class of application that can leverage things like the cache coherency between CPU and GPU and the system allocator that is present on Grace Hopper. And this application can have some part of the runtime happening on the CPU, another portion happening on the GPU. Data can exchange, but often one needs to access data on the other. We don't really move data. And this is a really completely new class that we haven't explored quite yet. And we're very excited about it because it can open a new way of accelerated application. Obviously, we run several real applications internally in our lab to measure Grace Hopper performance. And we see a speed up between, 2 and 3x, even more, moving from x86 Ampere to x86 Hopper, and then Grace plus Hopper. It's not just about HPC. Grace Hopper is also a great platform for AI training and AI inference, in particular for those AI-intensive tasks that require huge amount of memory, like large language model. They can use, for example, the CPU memory as a pool, while the GPU is busy computing, updating the neural network, and progress with the training task. So a lot of use cases in large language model, recommender system, databases, graph neural network. So it's very exciting, and we just started to explore what can be done if frameworks are tuned and extended to leverage Grace Hopper at its best. There's way more applications that we tested internally than one we are able to show in these brief minutes together. So stay tuned for news coming from NVIDIA, our partner, about the good that Grace Hopper can deliver to developer and customer in terms of performance, TCO, and overall time to science.